Hey everyone, welcome to Digital Audio 101 with our instructor, Michael Goodman. Michael is the founder and CEO of CEntrance Technologies, which has brought to market some of the most capable portable gear that we now find in hi-fi. Let's give a round of applause to our presenter, Michael Goodman.
And Michael Goodman, let's just dive into it, shall we? I presented this in at the Canjam in LA in October. It has been modified slightly since then. I don't know if you were there, but there's some changes for the better, mostly for the better.
Everyone
all right.
here in the back? Everyone's good?
Do you need me to take a microphone? No? Okay. Sorry. All right. So we're going to talk about digital to analog converters. And we're going to talk about them from the standpoint of not just the math, actually not a lot of math, which would be extremely boring, but we're going to talk about it from the standpoint of like how does it help listen better, right? And what biases are there from the manufacturers. The topics to address: is digital evil? Clock jitter. From A to D and back. Then we're going to talk about the DAC topologies, different ways you can make a digital to analog converter. We will talk about power hygiene, how important it is to have good power inside of a DAC. And then we'll talk about what's called house sound. Does a product from a different manufacturer sound different? In fact, the dual DACs sound the same. So that's our syllabus for today. About us, real quick, we've been a design house. Our company was a design house. We designed for technology for other clients, mostly in the professional audio business, over 120 clients in pro audio, 150 actually. I got to meet a lot of famous musicians like Herbie Hancock and Joey DeFrancesco through that effort. In 2009, 9 years into it, we became a product brand. So we took all the technology that we've designed for other companies and we started making our own products carefully without stepping on the toes of those people that we just consulted for. And now we have dozens of products in both pro audio and hi-fi. And these are the stereophile editor, Mr. We were just talking about him. The stereophile editor. Anyway, and then the absolute sound editor that I also got to meet. Production and listening. These are the things that we make. So we pretty much focus in portable products. That means John Atkinson, by the way, is the editor of Stereophile. MicPort Pro is a small cigar-shaped recording interface that we make for actors, podcasters, voiceover narrators. They travel with it. It's got a battery inside. It allows you to record voice narration anywhere. They love it. We have a Portcaster product, which is another version of that, also for podcasters, and like a whole bunch of other small little things that record audio. We also have products that play audio back. Hi-Fi Mate V2, you can see it on the show floor. It's a DAC, portable DAC with a battery inside, with USB-C input as well as a balanced Bluetooth input. So you can go into the DAC from your phone either with a wired connection or a wireless connection, and the sound quality is going to be awesome both ways. Now this DAC also has a power amplifier built in with 1.6 watts of output power and 4 headphone jacks. So you can go 1/4 inch, 3.5 millimeter XLR, or 2.5 millimeter balanced. Quite a versatile product. And then a newer product that we just introduced at this show is an amplifier, analog amplifier, with 6 watts of output power. Why, would you say? Well, because there's a whole bunch of planar headphones out there that are very hard to drive. You need a desktop amplifier to plug your planar headphones into, otherwise it won't be loud enough. But a lot of people that we deal with, because we make portable things, are people who travel, people who maybe, they commute, maybe they get on a plane and they go somewhere, and that's going to be more and more as we, return to normal. So portable amplifier that we made has 6 watts of output power, can drive pretty much any planar headphone under the sun. Again, balanced and single-ended, and it's a pretty cool little product. You can check it out in our. All right, is digital a servant or a frenemy? That is supposed to be A. All right, it's an appropriate question in the age of intelligent machines, isn't it? Let's take a look at that real quick. Analog versus digital. All right, so analog analog signals are smooth, they're slow, they're gentle. Digital is essentially a high-speed chase. Okay, why is this important? Analog doesn't need upgrading. Analog technology can work for 10, 20 years and not require a change. Digital is a blessing and a curse because it's a constant stream of upgrades, right? You have to buy a new iPhone every couple of years. Analog can do with one transistor, meaning you don't really need a lot of technology to process analog. With digital, you need billions of transistors, and every year you seem to need more and more. So very different types of technology that are used today. So analog is just to talk about getting from analog to digital, right? Analog is a slow, considered flow of electrons. They don't bounce around that much. Analog flows mix and coexist easily. This is I'm driving somewhere with this. Analog is distributed and ungoverned, right? It's a whole bunch of clean waveforms. A digital is a cacophony of cultures, right? There's a whole bunch of stuff happening on a computer motherboard, and there's a lot of interference in a computer motherboard, and consequently, in any digital product, you're going to have a lot of interference. You're going to have a lot of different things happening all at once. That creates a problem for sound quality. We're going to look at that in a moment. Digital requires order and police, and digital is ruled by a central clock. Okay, that's how you make digital work, is by basically making sure that all the chaos of digital signals, billions of transistors, everyone saying something to someone else, to some other transistor, all of that has to be policed. There has to be a central sort of highway, central clock, central way of communication that makes all of that work. Without that, it doesn't work well and consequently doesn't sound well. So what we're going to talk about is how to make a digital product sound good, despite the fact that there's lots of noise around inside the digital product. So what is mixed signal design? Mixed signal design is pretty much what everybody on the trade show floor has to be good at, and hopefully is. And that means that you're designing a product with both analog technology and digital technology in the same box. Possibly the hardest electronics discipline, actually. It's all about interference management. So this is what everybody here is focused on when they're back at the lab and not at the trade show floor saying that, oh, this is the best. When they're back at the lab, it's way far away from that. Quiet signals essentially must coexist with multiple sources of noise. That's what's happening inside of a digital audio product, any product. And the management of that is a trick. And we will dive into that in a moment. Why does audio attract people with a knack for crisis management? That's an interesting question. I know a lot of live sound engineers who are essentially crisis managers. They're really good at performing in an environment when everything is going to heck. Basically, there's feedback on 20 channels. There's screaming guitar players saying, "More me, more me." And the more guitar players, the and then so audio somehow is a discipline where people who know how to deal with chaos thrive. Let's talk about the central clock. This is one way of policing the complexity inside of a digital product. So at the heart of any digital product is a clock. It's a heartbeat. And then all of the information inside of a digital product moves to this beat. So the illustration here, this is a sine wave, this is an analog signal in blue, and then in green is a clock. It's basically a repeatable tick, 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 tick type thing that creates some order inside of it. A joke about clock quality. As we know, a broken clock shows correct time twice a day. And that's typically said by a marketer. The problem is with the rest of the day, is usually said by the engineer. So consequently, if you look at engineers versus marketers, which is an interesting dilemma pretty much in every company, if engineers ruled the world, everything would be working and boring. And if marketers ruled the world, everything would be rosy and broken. So we need both. Clock jitter. What is clock jitter? That which makes music lifeless. So it's important to know about clock jitter. So we talked about clock being this policing element inside of a digital product that makes sure that everything works in sync, essentially. When that's not happening, we have some problems that result in bad audio quality. Let's look at that. So this is normal clock, okay? Essentially, again, an analog signal and a digital clock that essentially happens at the same time. Let's look at a problem area, okay? Bad clock. If a bad clock was to crawl into a digital product, we would start having artifacts. How would a bad clock happen? Well, basically by some sort of a delay, some sort of a noise event that blocks the continuous solid action of a clocking mechanism. All right, so if that happened, right, so instead of this green periodic signal, you would have some sort of a delay, right? Okay, and then maybe another delay. So the clock would be irregular. How would that look like for the analog signal? Right, so basically the delay to the clock would affect this region here, and then that region there of the analog waveform. And the way it would affect it is it would essentially delay it. So this is the type of distortion that we would experience if, so basically how does the analog, the digital get converted to analog? Every time there's a clock pulse, a portion of analog information is sent out. So if you send it out later, you will get distorted information. So instead of having this nice little sine wave, you'll have a sine wave with a bump. And that is actually clock jitter. Wounded by jitter. That's our sine wave that is no longer true. So what does jitter sound like? Well, here's what it looks like. It looks like a Picasso. Basically, it's a result of audio being reconstructed incorrectly. It sounds unnatural. It's not true to the original recording. Now, jitter is a very particular type of distortion, which results, as I said, in a lifeless recording. You can't really pinpoint exactly how jitter sounds, other than you just want to turn it off. It's just uncomfortable. It's just not real. It doesn't let you plug in and experience reality. It just sounds computery. So it's difficult to deal with because you can't quite put your finger on it. So how do you clean it up? That's a very important question for anybody on the show floor who is designing digital audio equipment. First of all, you choose very accurate clocks, right? Well-controlled clocks. Then you make sure that all of the components inside of your product have good jitter reduction. Because you can have components that promote jitter, you can have components that reduce jitter. Careful power supply design, extremely important in creating a low noise baseline for the entire product. Low interference PCB layout, that's a technique that deals with how components are interconnected. And then good analog digital separation, so they kind of have to live in different worlds. Let's talk real briefly about A to D conversion, and then we'll talk about D to A conversion. I'll see which type of D to A conversion is better. So, in order to take a sine wave, which is this blue line here, and then convert it to digital, right? This is during the recording process, when they record music into a digital medium. Every time a clock strikes, a measurement is taken, and then that value is recorded. So we record the level of the sine wave here, then we record it here, record it here, record it here, etc. Now, the resulting string of numbers is essentially your digital information that corresponds to the original analog sine wave. So a period of sample and hold is essentially what happens when that measurement is taken. So you measure, and then you measure again, and then measure. While you measure, you actually hold the value. Each level is converted to a binary code in the system. Now, data transmission. So we have these numbers that we've just measured, a whole bunch of them, and then we have to transmit them to another side or record them onto a SD card, hard disk, etc. With analog, one chip sends a changing voltage to another chip instantly. So with analog, when you transmit from one analog circuit to another analog circuit, it happens instantly. Basically, it's a voltage that just gets transmitted. No delay. Zero latency, as they say. With digital, one chip sends a bunch of numbers to another chip on a schedule determined by a clock. So with digital, you inherently have what's called latency, which is a delay of transmission. What's a comparator? A comparator is a fundamental building block that helps you build an analog to digital converter. So it's the simplest analog to digital converter. It makes a 1-bit conversion, and if one signal is higher than the other, then the comparator changes the output state or trips. It produces either 1 or 0. Very quickly, that's the basis of what's called a flash A to D converter. So it's a whole bunch of comparators that measure the input voltage and then create a digital number that represents that voltage. All right. There's some pros and cons. It's fast, it's simple, it's most analog, including its sounds analog, but it's larger and it's got lower resolution. It can get expensive. There is a version of this technology on the digital to analog side, which we will look at, which will also happen to have the same pros and cons. Later in this talk, we will talk about delta sigma versus R2R architectures of D2A converters. A big question right now is like, which one's better? This is how we're going to get to describing the differences, the pros and cons, and the sonic differences that they have. Okay, so this is the A to D conversion process. Really quickly, just to get the background out of the way, most people already know this. A decimal number is something like that, and a binary word, just a string of ones and zeros. This in binary is the same as that 2021 in decimal. Okay. A couple more definitions and then we'll get to the nitty-gritty. Word stream versus bit stream. What are the differences between those two things? So, on a typical digital bus, a string of numbers gets thrown at the other side, gets transmitted. Numbers are streaming out on a digital bus created by one chip, listened to by the other chip. And a digital line, DSD, is essentially streaming out on a pin. This is we're going to get to it a little bit more in detail, but essentially the difference between DSD and what's called PCM is how the data is being transmitted. In a PCM situation, numbers are transmitted every once in a while. In a DSD situation, it's a continuous stream of ones and zeros. A PCM stream looks like that. We already saw that a moment ago. Whereas a DSD stream looks slightly different on the oscilloscope screen. Why is this important? A PCM stream is easier to reconstruct than a DSD stream. That's why DSD is not extremely popular. It's a better technology, but it's not yet very well widespread. We'll talk about that in a second. So, we've just talked about A to D technologies. Now we're going to talk about DAC technologies, D to A technologies. You are lucky because somewhere in a parallel universe, there's another version of me talking to another version of you, and that lecture has a lot more math. So you should be happy that you're in this universe right now. All right, to R or not to R, that is the question. Why is Ian McKellen here at age 82 playing Hamlet at Theatre Royal in Windsor, England? I don't know, but probably because he's good. So DAC technologies, there's 4 of them. Weighted resistor, R2R, big word these days, PWM, and Sigma Delta. We'll focus mostly on these 2, the R2R and Sigma Delta, because those are actually trying to duke it out right now, especially with a big fire at the AKM factory. We'll get to that in a second. Weighted resistor DAC. Oh my God, that's the parallel universe slide. For a 4-bit, Anyway, so a number is presented here, and a voltage is created at the output. That's all it is. Pretty simple, actually. Weighted resistor DAC actually reminds us a little bit of a flash A to D converter that we just saw a moment ago. Now, same pros and cons for this guy. Simple, quite fast, low interference, but it's expensive, and it requires a whole bunch of these operating amplifiers. So it's larger, lower resolution, not too practical. Okay, let's hold that in mind for a second. It's similar to flash ADC, as I just said. It's very similar technology. Okay, it needs a whole bunch of resistors, by the way. So these little things here are called resistors, and they're tiny little things that you put on the PC board. And their quality determines the quality of the DAC or the ADC. But you need a whole bunch of them, which is a problem for R2R designs. Okay, so the R2R DAC, which some people find smoother, works on that same principle of a whole bunch of resistors that are connected together, and then some of them are turned on and then turned off. And when you turn them on and off in a particular sequence, you get a number. You can essentially represent a number by turning some of those on and off. The resulting resistance is equivalent to R, which is the part of the name. Let's see here. Yeah. So R2R, the DAC that works on the R2R principle uses a whole bunch of resistors. It runs on a slower clock. That is good. You don't want a fast clock because that creates interference. You can also simplify the product and the PCB printed circuit board layout. It's easier math. It's easier to design and build. Does not need sophisticated chips. So it could be built as analog sound. So in general, the R2R DAC is easier to design, is easier to manufacture to a certain extent, and it doesn't need sophisticated chips. So those are the good things about it. Now the cons, the bad things about the R2R design, is it starts to become expensive the more precision you're trying to get out of it. So the moment you start getting to like 24-bit precision, you need a whole bunch of resistors, and that just becomes unwieldy. Your PC board starts to grow because there's just the farms of resistors sitting on that PCB. They'll have to be well matched. It's larger, and with smaller signals, it gets noisy because it gets bigger, so it gets more sensitive. Power sensitivity is an issue as well. All right, let's not talk about PWM DAC. Let's just jump right into Delta Sigma DAC. So the R2R DAC and the Delta Sigma DAC are the two competing technologies right now, or competing in the mind of a consumer, I would assume, yeah? They're not really competing, they just coexist. Delta Sigma DAC is a modern technology, more modern technology. A lot of people think that it's holy grail for audio. It's got low noise, low distortion, and it's inexpensive. And the way it does that is basically by employing a lot more math rather than just these blunt resistors that are just placed on the board. It involves something that's called Delta Sigma Modulator, which is subtractor followed by an integrator followed by a quantizer. I don't even know what this is going to sound like in a parallel universe. It's just going to be really complex, and we'll be here for 3 days. So it's a 1-bit DAC, which is important, not a multi-bit DAC. So instead of having a whole bunch of resistors, each resistor essentially being responsible for its bit. So if you have 24 bits, that's 24 resistors, but in reality more. Here you only have 1 bit, but that bit is changing really, really fast to try to catch up with the changing waveform. That bit is acting really quickly to represent a number in real time. So in a Delta Sigma DAC, there's a subtractor, there's a quantizer, etc., and a servo loop. Great. Here's the result of a Delta Sigma DAC. This is, if you were to look at the screen of an oscilloscope, this would be the analog input. That's the waveform that we hear. That essentially represents the movement of the air that hits the ear. The internal portions of the Delta Sigma modulator, the differentiator, the integrator, and the comparator are all doing their jobs. And essentially, at the output of the Delta Sigma modulator is something that looks like this. So it's a whole bunch of quick changes from 0 to 1, followed by a slow change, followed by some change, slow change, and it's some more fast changes. So again, if you were to look at the Delta Sigma modulated digital signal on the screen, it would correspond to the analog signal in a very strange way. So basically what it's doing, it's looking for changes. If there's a lot of change in the signal, it bounces a lot. And as there's less change, it kind of sits still, and as the change starts growing, it starts bouncing again. That's how the digital signal works. Why is this important? Well, the more bouncing, the harder it is to control the linearity and the quality of the signal. Delta Sigma modulation, the change in the signal, its delta, is encoded rather than the absolute value. So the more signal changes, the more information gets produced. And the result is a stream of pulses as opposed to a stream of numbers, as in the case of pulse code modulation, a different kind. The accuracy of the modulation is improved by passing the digital output through a 1-bit DAC and an analog signal, adding sigma, the resulting analog signal to the input signal. So in other words, they're doing a lot of math in a Delta Sigma modulator and Delta Sigma DAC to cover up the noise that gets created due to a lot of bouncing ones and zeros. Simple explanation. As I just said, reducing noise in Sigma Delta DACs. A 1-bit output is very easy to implement in hardware, as there are ways to make that 1-bit output have high signal-to-noise ratio. Oversampling, noise shaping, and dithering are 3 math techniques, algorithms, that are used to reduce the noise in a D2A converter, specifically the Delta Sigma D2A converter. We can quickly look at what they do. Quantization noise, essentially, is the type of noise that results from imperfect measurement. So as you measure the green analog sine wave, because you're doing it at the wrong time, there's a little bit of error that you essentially experience. That error can be represented on a graph. This is essentially the graph of the error that gets created as you make that imperfect measurement. Now that error can be canceled out in math, which is a great little benefit of the delta sigma modulation technology. There's also something called quantization noise, which can also be taken care of through mathematical filtering. And then there's a third one, it's called dithering. Dithering is easy to show visually again. So adding low-level noise to the signal in order to improve resolution at low signal levels. It's a technique, I think Sony came up with that, like in the, I want to say the 80s, late 80s. The picture only uses black and white dots. This picture right here only uses black and white dots. Yet it appears grayscale. You see this, right? This is how newspapers print, or used to print pictures. Who here remembers newspapers? Anyway, so if you look real closely, you'll see that the dots here, there are no gray dots. All dots are either white or black. But the fact that there's noise in between them, that creates an illusion of depth and grays and all that. Okay, so that's a similar technique that's used in digital audio to get rid of noise. Again, to represent dithering pictorially, which is one of the noise reduction techniques, a high resolution image of a kitty would have, you know, a lot of texture and the hair and all that, right, on the fur. Now, if you were to convert it to what's called a web palette, which is reduce a whole bunch of colors, it'll be low quality. But then if you add dither, like we just talked about in the black and white picture, you can still make it more believable, right, better. So that's how you take something that was analog, convert it to digital with noise and imperfection, but then with dithering, which is math, make it still more presentable. All right. DSD is essentially a faster version of that same thing. Noise shaping moves the noise out of the spectrum. We can go back there if anybody's interested. The pros of the delta sigma digital to analog conversion process is about 10 times cheaper to make than the R to R DAC. It becomes smaller. Delta sigma converter is smaller than the R to R converter because it doesn't require a whole bunch of resistors. Oversampling, which are all these math things that we just alluded to, they beat R to R in terms of noise. So it's actually lower noise. It's lower distortion, it's lower noise, it's smaller, it's easier for portable applications. This is where clever math wins over bulk of components. There are cons to the delta sigma DAC. It runs on higher speed clocks. So you really have to know how to do your mixed signal design, which is what we talked about in the beginning. Because the product now has the analog portion, analog circuit, and a digital circuit, and they have to kind of coexist, and the noises should not cross that boundary. It's almost impossible to roll your own delta sigma DAC unless you're using off-the-shelf chips. With the R to R DAC, it's actually pretty easy to make your own R to R DAC once you just buy a whole bunch of resistors and you arrange them on the PC board. Anybody can do that. It's going to be bulky. Here you need to buy a chip that already has that implemented. It requires a CPU, so it requires a programmer, a DAC that's based on delta sigma technology needs to be created with analog engineers, digital engineers, and most likely computer programmers. So you have to have a larger team or somebody, well, one person who knows all of those domains. And it requires more filtering at the output. So those are the cons of the delta sigma DAC technology. All right, and here we come to the good old shootout. So which one's better, R to R or delta sigma? Well, let's take a look. This is the Shootout. So we're going to take two chips, which are sort of favorite in the hi-fi community. The PCM1704, a lot of people swear by it. It's an R2R DAC. And the AK4490, which is a Delta Sigma DAC, which is probably the most popular chip right now in most of the technology out there. All right, maximum sample rate in the R2R DAC is limited at 96 kilohertz. It's pretty much unlimited with Delta Sigma at 768. Signal to noise wise, in terms of the amount of noise compared to the number of the amount of signal, they're the same. So that's parity. Total harmonic distortion, and this is where Delta Sigma, the more complex mathematical process, wins, because math allows you to clean that up. Now we get to the cost, which is probably the biggest determining factor. The AK4490 used to be $2. That was before they had a fire at the factory. Then it shot up to $100 if you were dealing with scalpers. And now they're bringing it back, fortunately, after 3 years. So that fire happened right before COVID. So a problem compounded on top of another problem. Fortunately, they just brought it back, and I think it's going to be around $4 or $5. Anyway, this is a workhorse of the industry. That chip was and will become again once they restart manufacturing within the next couple of months. And then this chip was obsolete. It was obsolete back in 2019, so before COVID, before everything. So essentially, the Shootout here demonstrates that the Delta Sigma technology won in terms of cost and in terms of audio quality. Now, since AKM had a factory fire and AKM chips were unavailable for several years, guess what the audio industry started thinking? R2R is better. Well, because it was available. But that thinking will be shifting again soon, because the Delta Sigma DACs are going to be available again pretty soon. And unfortunately, that equation does not really bode well for the R2R technology. All due respect, it's a great technology, but this is just so much simpler to do these days. All that math is already inside that chip, and it's $4, compared to 30. Really quickly about power hygiene. So this all ties together with regards to how do you design the product that is a D2A converter, that's a DAC, right? Any sort of a digital audio product. Make sure clock noise doesn't get into audio. Okay. Make sure power supplies are separated. So there's a separate power supply that has to be made for analog, and another different power supply has to be made for analog, ideally. These little things, there's like 7 power supplies in them, because every chunk of the circuitry essentially gets its own power supply so that no contamination happens between analog and digital. That way you can get the noise down. Make sure grounds are separated, and watch for EMI interference on the PCB itself. So a fourth domain that is required in designing a good mixed signal product is a mixed signal design architect or PCB layout architect who really knows all this. So we're talking about analog electronics engineer, digital electronics engineer, a software engineer, and a PCB engineer. So 4 domains need to be covered if you really want to make a high quality analog to digital converter, digital analog converter, or any sort of a mixed signal design. Now, this is weird. We're striving to get our DACs to 0.0001, maybe? That's current sort of state-of-the-art in DACs. So basically 3 zeros after the decimal point. All the while, speakers and headphones, you know what their distortion is? 1%. Dan Clark was here a moment ago, and I'm using his laptop. Okay, so I am indebted to Dan. I respect the man, and he's a friend. But unfortunately, and his headphones are better, right? But unfortunately, they're still in this range, 1 to 10% of distortion. So 3 orders of magnitude is 1,000 times. Headphones have 1,000 times more distortion than DACs, which is mind-boggling, unbelievable, right? So even a DAC that's 0.001 is 1,000 times better than a typical headphone. And speakers are even worse. We don't know that. So do we really need to push for less total harmonic distortion, which is just a fancy word for distortion in DACs? We do have a fundamental discontinuity in 2 different components. A DAC is extremely linear. Well, when we're listening to it on the headphones or speakers, we're not even hearing the DAC. We're hearing the speakers and headphones, which is why it's important to listen to a whole bunch of headphones and a whole bunch of speakers, because that's how you can sort of average out and tune out the differences between them. Okay, that's a little interesting little tidbit about where the problem areas lie. Transducers are hardest to make still. All right, last topic here is house sound, right? Is there such thing as house sound? Does a DAC from one company really sound different than another DAC? Everything that we've discussed up until this point, which had to deal with the quality of design, noise, power supply, PC board layout, cleanliness of the whole design, that all has to come into play. And therefore, yes, indeed, depending on the quality of the design team at a particular manufacturer, you will have different results.
I have a quick question.
Yeah.
So I'm guessing, just like where the inconsistency is coming from, because if these Delta Sigma DACs are using the same bit microprocessors and they're using the same algorithms for dithering or on the input, shouldn't the performance be the same throughout all DACs that use Delta Sigma and use the same bit microprocessors?
Right, quick recap. So if all Delta Sigma chips use the same math inside, wouldn't all DACs be the same, right? Okay, so as I was just saying a moment ago, there's a lot of stuff that happens around the chip that you buy for the $5 from the distributor. And that stuff is the power supply that supplies the power to the chip. If that power is not clean, then the chip will not perform to its specification. So the chip is designed to essentially work with absolutely clean power. The chip is also designed to experience zero interference from other chips that might be next to it, also essentially ringing, buzzing right next to it, right? So that's the cleanliness of your PC board design. So there, we're just talking about somebody who just buys the DAC chip off the shelf, but puts it on the board in a suboptimal way, not really knowing how to connect it correctly, and therefore that design is not going to sound as good as a design that was designed by somebody who does know how to interface correctly.
And that would be a difference between a $30 DAC and a $3,000 DAC?
Very easily so. We're not going to go into, whether there's a big difference between a $30,000 DAC and a $3,000 DAC, just like with cars, right? The quality of the car really changes as you go from like $5,000 to $10,000 car, right? And then as you go to a $50,000 car, okay, it's different. $500,000 car is not that different, even though there's a huge jump in price. Same with DACs, right? So when you get to a certain level of price, the quality of the DAC is probably going to be already way better than any headphones you're going to throw at it. And if you're, doubling, tripling, quadrupling the price of that DAC, again, the difference is going to be minimizing, getting smaller and smaller and smaller, right? But like a $30 DAC, $300,000 and $3,000 DAC, I would expect there to be quite a bit of difference in terms of cleanliness. I mean, it's noise, it's distortion, it's the engagement, it's the musicality that you experience when you listen to it. Does it allow you to lose yourself in the music and forget that you're listening to the headphones and actually think that you're right there with the musicians? Or does it sound buzzy, mechanic-y, metallic-y, weird, unnatural, right? Which is, for example, a $9 Apple dongle, right? The cable that you plug into the lightning jack and it gives you a headphone output. There's a tiny DAC inside. Not so good, unfortunately. Pair that up against any DAC here on the show floor and you will immediately hear graininess. You'll hear some sort of weirdness, you know. A lot of these things can't really be described because, as we talked about, the digital noise doesn't have a good representation in the analog world because we don't process audio the way that computers process audio. So therefore, the little glitches that happen in computers don't really have a good explanation. You can't really say, oh, it's lifeless. Yeah, I guess it's lifeless. All right, so clocking, power supply, PCB layout, op amps, and analog filters, all of that matters in the design of different DACs. And lastly, of course, it's marketing. Because at the end of the day, different companies will describe their products differently, and a lot of consumers will be like, well, it was described better, so therefore it's better. 3 product development rules real quick to finish up with. Someone will always get ticked off. I've designed hundreds of products, okay? I know that someone will always get ticked off, so I don't get ticked off anymore. Those people don't pay your bills, which is important to kind of help, you know, breathe and move on. And then most importantly is focus on those who like your stuff. I studied sound engineering at Columbia College in Chicago with Malcolm Chisholm. Malcolm Chisholm was an amazing sound engineer who is known to be uncatchable. Essentially, nobody can catch up to Malcolm. Why? Because Malcolm recorded a Chuck Berry record, like I think it's Johnny B. Goody, that is actually traveling right now in space on a Voyager 2 as part of the Best of Earth capsule that they placed on that spaceship, and it's like a million years away from Earth right now. That's why nobody can catch the guy. You know, he essentially created the Best of Earth. He contributed to the Best of Earth. Chuck Berry's pretty good. Used to be. Yeah. Anyway, and then so Malcolm said this. So this guy, right? He said this: no matter how good you are, somebody will always hate your stuff. Relax. It's a good little life lesson. All right, we talked about what we do. Questions?
Yeah, I just got a couple of questions. I'm seeing some stuff that contradicts some of the things you're saying. For instance, there's some higher end RQR DACs that are claiming, thank you. I see where there's some RQR DAC companies, especially some Chinese-made ones, that are claiming something different. They're claiming that their measure specifications are equal to the delta signal DACs, and in fact, they've been measured to almost equal them. So that is one question I wanted to ask you about. And the other question is about the percentage of distortion you're showing on the headphones. I'm seeing some of the manufacturers who are out on the show right now, on some of their web pages, claiming much lower distortion than what you're saying. So I just wanted to see if you could comment.
How much lower?
Yeah, I'm talking about the distortion on the headphones. You're claiming 1 to 10%, those in speakers.
That's typical, yeah.
Yeah, but I'm seeing some of the manufacturers' claims out here on the floor, people who make headphones on some of their websites claiming much lower figures.
How much lower?
I can't remember exactly without looking at the website, but I know for a fact it was way under 1%.
Way under 1, possible, and that's why I mentioned Dan Clark. He's actually pushing the boundaries right now. He's doing the work right now in modeling the way the transducer is moving. Still not 0.0001, so that still holds.
Right.
As we improve headphone technology, it will get better and better and better. But still, the dichotomy is there, right? That the huge difference between what's achievable in electronics and what's achievable in transducer technology, that's still there. And then your first question was how is it that some manufacturers claim that their R2R designs are better. Two things. Well, of course, marketing. But prior to that,
It's not just marketing though, it's measurements from people who have,
right,
you know, they verify this one.
right. I'm getting there.
Yeah, okay.
Okay, so we were talking about R2R DACs, and we talked about cons, okay? So R2R DACs are expensive due to the need to have lots of well-matched resistors. But if you do pay for lots of well-matched resistors, you can actually do a good job. It's just going to be very complex, logistically, not mathematically. It's larger, and it's still noisy with smaller signals, and you have to have stable power. So essentially, if you throw a lot of money at an R2R DAC, you can make it approximate the behavior or the performance of a Delta Sigma DAC. But if a Delta Sigma DAC is available, and let's say there was no fire at the factory that makes the Delta Sigma DAC, then the Delta Sigma DAC is just so much simpler to implement. So in a way, right now, as I mentioned, the resurgence in R2R DAC popularity is due to one very, very simple reason, and that is the fact that the Delta Sigma DACs suddenly disappeared for several years, and now they're going to reappear, and you will see a whole bunch of R2R DACs essentially become less and less prominent. Does that answer your question?
Okay, thank you.
Any other questions?
Yeah, I think we have time for just one more. All right. Well, everyone, please thank our presenter today, Michael Goodman.
Our company name is CEntrance. Right there. If you come up with a question, you want to go talk, that's fine. Thank you so much.